You know, every single day, scientists are just generating mountains of data. We're talking genomic sequences, new chemical compounds, you name it. So the big question is, how do you actually turn all that raw information into, say, life-saving drugs or brand new materials? Well, today we're going to look at a blueprint for what's called discovery intelligence, a system built to do exactly that. It uses AI to find that one crucial needle in a cosmic haystack. Let's follow the data and see how it works. It all boils down to this one huge question. If you were tasked with building an AI that could help find a cure for a disease, or discover new sustainable materials, or predicts climate patterns faster than any human possibly could, where would you even start? You'd start with a blueprint, an architecture that looks, well, yeah, like this. I know. At first glance, it's a bit of a spaghetti monster of boxes and arrows. But trust me, there's a really clear, logical story being told here, and we're going to untangle this thing together, piece by piece. So the best way to wrap our heads around this is to treat it like a journey. We're going to follow one single piece of data from its messy, raw beginning and track it all the way through the system until it pops out the other side as a genuinely useful prediction. And that journey, it doesn't start with fancy code or algorithms. Nope, it starts with the raw ingredients. The very first step is all about sourcing and acquiring the data, basically finding and gathering the fuel for our AI engine. All right, back to our map. See this first yellow section? This is where it all kicks off. You can think of this system as a voracious reader. It pulls in all this information from structured databases that are full of chemical data, but it's also scraping and trying to understand unstructured text from millions of scientific papers and patents. It's grabbing everything. And just to be super clear about what's coming in, you've got this neat, organized data from databases like Chembl. It's packed with great drug discovery info. But then you have the wild, untamed data from scientific literature and patents. So the system's first major challenge is to understand both the clean, structured stuff and the messy, unstructured stuff, and somehow bring them into the same world. Okay, so once we have all our raw ingredients, we can't just throw them at the AI model. They've got to be prepared first. And that brings us to the system's prep kitchen, the data lakehouse. Let's zoom into this blue section here. The data lakehouse is where all that messy, varied data we just collected gets completely tamed. Its entire job is to take this chaotic flood of inputs and forge it into a clean, high-quality, and totally reliable stream of information that's ready for the AI. So what in the world is a lakehouse? Well, it's actually a really clever hybrid. You get the massive, super cheap storage of a data lake, which is perfect for just dumping huge volumes of raw scientific papers. But you also get the powerful management and organizing features of a data warehouse. Basically, you got the best of both worlds, massive scale and perfect structure. It's critical for this kind of work. Now, inside this lakehouse, the data goes through a 3-step makeover. First up, it hits the landing zone, completely raw and untouched. Then, in the staging zone, powerful data processing engines like Apache Spark get to work, cleaning it all up and converting it into a super efficient format. And finally, it arrives at the feature store. At this point, it's not just data anymore. It's been carefully engineered into the specific features and graph structures our AI model actually needs to learn from. All right, our data is prepped and ready to go. Now we can finally move to the heart of the whole system, the MLOps platform. This is the AI brain, where the real intelligence gets created. Now we're in the pink section, the MLOps platform. MLOps is just a fancy term for making machine learning less of a messy art project and more like a reliable, automated factory assembly line. And what's really cool here is that this is a full-blown factory for building models. It uses tools like MLflow to track every single experiment and make sure that only the absolute best models ever make it through. So how does this factory actually work? Well, first, that feature data we made is fed into something called a graph neural network. It's a special type of AI that's amazing at understanding relationships, which is perfect for things like modeling molecules. As it trains, the MLflow server is like a meticulous supervisor, logging everything. The best performing models get put into a registry, but before any model can be promoted, an automated evaluation service stress tests it to prove it's actually better than the current champion. It's a tough competition. Look, an amazing AI model is totally useless if no one can actually use it, right? So the final parts of our journey are all about getting its predictions to the user and, this is critical, learning from those interactions to get even smarter over time. And this is where it all comes together. The green serving layer is how a prediction actually gets from the AI to a scientist. But the real magic, in my opinion, is that purple feedback loop. This is what stops the AI from becoming obsolete.
It creates a living, learning architecture that is literally designed to improve itself.
So the winning model, our champion, gets packaged into a container using tech like Docker. Think of it like putting the AI into its own little self-contained suitcase with everything it needs to run. That means it can be deployed anywhere. A scientist can then just ping it through a simple API, send a question, and get a complex prediction back in milliseconds.
Now, this might just be the most important part of the entire system. Every single prediction the model makes is logged. The system constantly monitors this stream of new data to detect something called drift. Drift is basically when the real-world data starts to look different from the data the model was trained on. If that happens, it automatically triggers an alert to retrain the model on the new data, which keeps it current, accurate, and relevant.
So let's just do a quick flyby of that incredible journey. Our data was acquired from all over the place. It was cleaned and standardized in the lakehouse. Then it was engineered into specific features, used to train and select a champion model, deployed out into the world to serve predictions, and finally, the system learned from its own work to start the whole cycle over again, but smarter.
So when you see it all laid out like that, you start to realize this isn't just a technical diagram. It's a recipe. It's a recipe for building an engine of discovery. And it really just leaves you with one big question. If you had an engine like this at your fingertips, what massive scientific problem would you point it at first?